In previous lectures, we saw regression where we're comparing one quantitative variable to another quantitative variable. But a really useful application of regression analysis is when you have a factor covariate and you want to be able to detect differences in a quantitative outcome with respect to that factor covariate. So the key idea here is that the outcome is still going to be a quantitative variable, but the covariates we're going to be using in the model are factors. And so rather than fitting a continuous line, we're going to be fitting, averages to specific levels of the factor. And so fitting lines is equivalent to fitting means when you're using this sort of factor modeling approach. And so it's kind of nice because we might want to be able to evaluate the contributions of all the different factor levels at once, in addition to being able to determine specific differences between specific levels of a factor variable. So the example that we're going to be using is data from movie ratings on Rotten Tomatoes. So Rotten Tomatoes is a website where people can go online and rate movies. Those movies are also rated by critics and so forth. And so each of the movies, as you can see here, has a Rotten Tomato score that's between 0% and 100%, where 100% means it's a great movie and 0% means it's a pretty bad movie. And so this data set is actually available from this Rossmann-Chance website. And so I'm downloading the data here using the download file command and then reading the table in to R. And so if I look at the data set, I actually see that it has the titles of the movies. So these are sort of famous movies. And then they have their score on Rotten Tomatoes as well as their rating. So PG, G, PG-13, and R. The genre that the movie comes from, the box office gross, as well as something about the running time. So one thing that we can do right away is we can make a plot where we show the movie score, the Rotten Tomato score by the movie rating. And so again, I'm going to be using this jitter command. And so all I'm doing there is, you can imagine I'm plotting all the movie ratings for the G movies here, for the PG movies here, the PG-13 movies here, and the R movies here. And to make it a little easier to see, I just jitter the X value a little bit so you can see that they're a little bit spread out. So this is the Rotten Tomato score by the rating of the different movies. And the first thing that you could imagine doing is you could actually just calculate the mean ratings for the movie. So that's what I've done with this t-apply statement here. I take the movie score and I break it down by the movie rating, and within each level of the movie rating I apply the mean function, and then I plot those mean ratings. And so I can see that for the G movies there's a slightly higher mean rating than for the others. But an important point here is that the mean rating, although it's higher, is based on a much smaller number of observations for the G movies than for the other types of movies. And so another way to write it down, other than just calculating a mean for each group, is we could say, so suppose I have a score for the ith movie. That score is related to this sort of linear model. And so again, this is going to it's just like fitting a regression line, but where we include a slightly different kind of variable. So we have this B0 is now going to be the average rating for movies with a G rating. And then what we do is we add a term that's an indicator variable. So this indicator is sometimes called a dummy variable. And what it means is it's a dummy because it's standing in for a logical variable that says, okay, if for the ith variable the rating is PG, this variable is equal to 1. If the ith movie has a rating that's not equal to PG, this variable is equal to 0. And so the same thing for this one. If the movie is PG-13, this variable is equal to 1. If the movie is not PG-13, it's equal to 0. And the same thing for an R rating here. And so what we can then do is we can actually figure out what the average values are from this linear relationship based on the coefficients that we have. So B0 again is the average of the G movies, because if you're a G movie, this is 0, this term is 0, this term is 0, this term is 0, and all you get is B0. B0 plus B1 is the average of the PG movies, because if a movie is PG, this term is 0 and this term is 0, and you only get B0 plus B1, and this term is now 1. And similarly for PG-13 and R, you get B0 plus B2, and B0 plus B3 is the average values. So this seems like a slightly more complicated way to write it than to actually just calculate the average. And the reason why we're going to do that is because when you do this slightly more complicated thing, you're able to fit these with linear models, and that allows you to be a little bit more flexible in the way that you fit the models. So here's how you do it in R. So we have the movie score variable, and then we fit a linear model relating that to the movie ratings. And we're going to coerce them to be factor variables. And the reason why we do that is because we don't want them to treat them as quantitative variables. In this case, these are characters in R. But in general, they might not be characters, and we need to coerce them to be factor variables so that R knows to treat them as calculating averages rather than treating them as a continuous variable and trying to fit a straight line through them. So then we can look at the summary of this object, and we get an intercept estimate, and then we get estimates for each of the different movies. So it looks like this is the G movie average rating is 67.65, and then you can see that if you have any other rating, you have a slightly lower value, and so that you know that because say, for example, if you're a PG movie, your average rating is 67.65 minus 12.59, and so that you have a slightly lower rating. Here, none of the p-values are significant, and the t-values aren't very large, and that's because I think, at least in part for this data set, because there are so few points among the G ratings that it's hard to tell if we've actually observed a big difference or not. So we can actually plot the fitted values. So again, here the data points represent the movie ratings versus the movie scores from Rotten Tomatoes versus their ratings. And you can see here now are the values that you get from fitting the linear model, and they're the values that you would expect. They're sort of the means within each group. So that sort of looks a lot like what we did with the mean variable a minute ago, but by using the linear model, we're able to use a lot of the sort of the nice framework that's been built up for doing statistical inference. So the first question that you might want to ask is something about what is the average difference in rating between G and R movies. So in that case, we can actually get the average rating for G movies is just equal to this B0 term, and the average rating for the R movies was B0 plus B3. So if we want to get the average difference, we do B0 plus B3 minus B0. We just get the B3 term. So it turns out that in R, we've actually already calculated the B3 term. That was the coefficient on the R ratings down here. So that's B3, and we actually already have its estimate of its standard error and its t-value and its p-value. And so we can actually calculate a confidence interval for the difference in rating between G and R movies as minus 26.80 to 2.763. And so an interesting thing here is that this confidence interval covers 0. So 0 being the case where there's absolutely no difference between the score for a movie with rating G and a movie with rating R. So since it covers 0, it seems sort of unlikely that we've seen a very strong difference between the two ratings in the data set that we have. A second question that you might want to ask is, what is the average difference in rating between PG-13 and R movies? So now we're comparing PG-13 and R, and so PG-13 is B0 plus B2 is its average score, and so the average score in the R movies is B0 plus B3, so we have to subtract those two things and we get B2 minus B3. Well, it turns out from this standard linear model fit that we got using the defaults, we actually don't get an estimate of this term or its confidence interval. But what we can do is we can actually reorder our model or rewrite our model a little bit. So before we were letting B0, the intercept term, be the average rating for G movies. And now what we've done is we've actually just recreated a different set of indicator variables. So now we have an indicator for G, an indicator for PG, and an indicator for PG-13. And so B0 is now the average for the R movies. And so if we want to get the average difference in rating between difference in score between PG-13 and R movies, we actually now calculate B0 plus B3 and subtract off B0, and we get just that B3 term, which again we can actually calculate directly from our linear model. So the only problem is we need to get R to recognize that we've made this switch where we've made the intercept term be equal to the average score in the R movies. And so the way that you do that is you fit the same linear model that you had before, and you have this factor term for movies rating, and you just tell R what is the reference category. So the reference category is going to be the category that's used as the intercept term. So in this case, we tell it that R is the reference category, and we do our summary. And now we see that the intercept term is just the average rating in the R movies. And then we actually have the difference now between R and PG-13 movies is just equal to this B3 coefficient estimate that we have here, and we can actually calculate out the standard error, the t-value, and the p-value for that coefficient. So that's how you ask those sorts of questions, and you can actually use the confidence interval confident function to actually calculate the confidence interval for the difference in average rating between PG-13 and R movies, or average score, sorry. And you can see that the average score, again, confidence interval covers 0, so it's unlikely that there's a major difference in average score based on the data that we've observed. So the third question that you might want to ask, and this is where it kind of the linear modeling framework comes into its own, is what if you want to know if there's any difference at all between any of the different levels of this particular variable? So this is just one variable, this ratings variable, and you want to know if the score variable is associated sort of significantly with this variable at any level rather than any of the individual levels like we've done before. So we've tested sort of these individual coefficients, but suppose you wanted to sort of look at all three coefficients at once, B1, B2, and B3. And so you can do that using what's called ANOVA, analysis of variance. And so in R, the way that you do that is you first just fit the linear model just as you did before. So we have a linear model where the outcome is the movie score and where the covariate is equal to a factor variable, that's the movie rating. And then we just apply the ANOVA command to this LM object, and we get what looks like what's called an analysis of variance table. So what we get out of this analysis of variance table is a few different things. So if you look at this table, the degrees of freedom tells you how much is, in the case of this variable here, the movie's ratings variable, the degrees of freedom tells you how many parameters that you had to estimate for this variable. So in this case, there are 3 parameters that we had to estimate. And then the residuals is the number, the sort of the length, the number of movies minus the degrees of freedom that we had to use to estimate the variables that we care about. And then I'll talk about the sum of squares here in a minute. And the mean square is just the sum of squares divided by their respective sort of degrees of freedom. And then the f value is the ratio of these two values. And then we get a p-value here at the end. So an important point to know is that this f value can't be interpreted as on the scale of a difference, just like in previous examples we were looking at the coefficients estimates B0 had and B3 had and so forth. And in those examples we actually could interpret those on the scale of the averages of the movie scores. Here this f value can't be interpreted in that way. But this p-value has the usual properties where if there's absolutely no difference across any of the rating levels, this will have a uniform distribution, and it'll be slightly less than the uniform distribution if there's something going on. And so a p-value of 0.43 doesn't suggest that there's a very, very strong difference between the different categories. So just to give you a little bit of an idea or an example about how the sum of squares works from the previous slide. So the f statistic is actually a ratio of this mean square for the factor variable divided by the mean square for the residuals. And so the mean square for the factor variable in this case is going to be actually equal to something about the sum of the distances from the fitted value in the G movies, that's the blue value here, to the overall average, this red value here. So for each of the data points, it's the same distance here in a factor model, and so you're going to sum and square those distances. And then the denominator term is actually the sum of squares for the residuals. And so what that is that's the sum of the distances from the actual data points to the fitted values, so that's these blue lines. and so we're going to sum those up and square them. And so if the fitted value is really close to the data points, these residual terms will be very, very small. That's the denominator. And then the numerator is how far away the fitted value is from the overall average. So you can think of it as how far did we have to move within this group to get a really good fit. So if those numbers are very big and these numbers are very small, then we have done a very good job of moving this line to fit the data points. And so that's a little bit about how those sum of squares work, although understanding that is a sort of a class unto itself. Last, I'm going to talk very briefly about Tukey's honestly significant difference test. So this is used, I would say, somewhat less frequently than just a basic ANOVA. And so what this analysis does is, again, it's a sort of an ANOVA analysis. This is another way to perform an ANOVA is using the AOV command, where again I've related the movie score to a factor variable for the rating. And then I can apply this Tukey HSD command to it, and what it's going to do is it's going to calculate the differences between all possible pairs of factor levels. So here PG versus G, PG-13 versus G, R versus G, and so forth. And it gets all the possible differences. It gets lower and upper confidence bounds for those differences. Again, at the 95% level, but now it's the 95% level where we're talking about a family-wise confidence interval. We'll talk about that later in the class when we talk about multiple testing, but basically it means that we've adjusted these p-values that we see here at the end for the fact that we did a whole bunch of different comparisons. And so if we call p-value significant less than 0.05, we won't get a lot more false discoveries because we've, or false positive results because we've accounted for the fact that we've done all the possible comparisons. So this is used somewhat some of the time and is a conservative test, but if you're sort of looking to see if explore what are all the possible relationships between the variables. But again, I would say that ANOVA is a slightly more common approach to determining how a factor variable is associated with a quantitative variable.